Assalamu alaikum. Welcome to our VLSA2 project presentation. We are group number 31 and our project is asynchronous FIFO design. The objective of our project is to safely pass data from one clock domain to another. As a result, bulk data can be transferred by DMA across chip. Also, it will help us to interface with processor and bus system and communicating to off-chip component. This is the main block diagram of our FIFO design. Here, read and write clock has two different clock frequency. Write pointer always points to the next word to be written. Read pointer always points to the current FIFO word to be read. If the reset goes high, both pointers are reset to 0. As soon as the first data word is written to the FIFO, the right pointer increments. The empty flag is cleared. When the right pointer wrapped around all memory and caught up to read pointer, full flag goes high. Now, if the read pointer goes high, it starts to read and full flag goes low. After reading all data, empty flag goes high. For synchronous, we use two D-flop system. We pass the right pointer to a D-flop which is driven by the read cycle. And in the same manner, the read pointer is fed to a D-flip-flop which is driven by right clock. As a result, we get read pointer and synchronized write pointer operating under same read clock and same with write pointer and synchronized read pointer. So now we can compare them and derive a logic for generating empty and full condition. Also, to reduce metastability, we used binary to gray counter. Here is our code. In we can see that this is a write clock domain and this is a read clock domain. And this is the clock domain crossing where we use a 2D flip-flop synchronizer. In the test bench, we experimented three cases. First, data is written until memory is full, but no read operation. Second, data is read until memory is empty, but no write operation. Lastly, both read and write operation is implemented simultaneously. Next, my partner Prova will discuss the workflow of our project.
Here we can see our waveform in cadence simulation, and in our first test case we will write the data and we will keep the read signal to 0. And here when we have enabled the write signal in the negative write clock edge, the data has started writing, and after starting writing in the FIFO, the empty flag has been 0. And after a while, when we have finished our writing, the full flag will be on. This is our second test case where we will just read data and we will not write anything. That's why we have kept the write signal 0 all along, and we have enabled the read signal. And after enabling the read signal in the next negative clock edge, data read will be started. And after reading the data from the FIFO, after the whole process, empty flag will be on. This is our third test case where we will read and write data simultaneously. That's why we have enabled both of the read and write signals. And this is the thing that we have enabled the read signals first, but still data read hasn't been started. This is because we haven't written anything yet in the FIFO. So when we enable the write signal, the data write will be started, and then only data read will be started in the negative clock edge. We can see here both the read and write operation has been done simultaneously in this test case, and the frequency of data read is almost double of data write because of the different clock frequencies. Here we can see our RTL synthesized file. The summary report says that it has almost 31,000 gates. And if we zoom in, this is the universe layout of our asynchronous FIFO. Here we can see in the left hand side all the input pins are placed. In the right hand side, these are the all output pins. And this is the layout after all post routing, metal filling, clock tree synthesis, etc. As we can zoom in and see the little metal rails and other connections. If you observe the virtuoso layer switch, we can see our layout zoomed in on the polys and other images. Here we can see that our DOC check is completely error free. Thank you for watching.